All right, so now that we know what projectile motion is, let's talk about all the different parts of the shapes of this parabola that a projectile will make. So in projectile motion, we know that the path must be parabolic. That means that the path of a projectile has to make this really pretty shape. And it is a quadratic. Hopefully you remember that from algebra, that a parabola is a quadratic. So we know the path of projectile motion is quadratic. And we've got two-dimensional vectors. So we said that after we threw something off of the Leaning Tower of Pisa, we had gravity working on it. And then we had that horizontal motion as well. So we're going to be dealing with two different vectors in two different dimensions here. We have vectors on the y-plane, and these are our vertical vectors. So everything that deals with going up and down is going to be on this y-plane, and it's going to be these vertical vectors that we're going to talk about. The next type of vectors we're going to deal with are going to be our horizontal vectors. And those are going to take place on the x-axis. So it will help us divide them up and to label this parabola a lot better if we know what we're dealing with on the y-axis and what we're dealing with on the x-axis. So what about the shape of the parabola? Some parabolas are long and skinny. Some parabolas are super, super tall. Some are even on both sides. So how do we know what that shape is going to be? So the shape of a parabola depends on the initial velocity. So the shape depends on the initial, it'd help if I could spell, velocity. So depending on what that initial velocity is, depends on what shape we're going to get. So we have our velocity, our initial velocities right here. This is where we've launched it. And down here is our launch angle. We're going to call this angle theta, and that is our launch angle. So we have a larger angle up here. And down here, this long, short, fat one is when we launch it at a short angle, or a smaller angle, I should say. If you look down here, this theta only goes from here to here, but the theta for this large angle goes all the way from up here, and it wraps all the way down. So the shape of this projectile depends on the initial velocity. More than anything, it depends on this initial launch angle. That's the biggest thing that the shape of that projectile depends on. All right, so now we're going to move down here. Now that we know the different shapes are dependent upon what this vertical velocity is, how do we figure out what our projectiles, what its path is going to take? How do we apply what we know about kinematics to these projectiles? So we're going to move to the bottom half of our page. And you can see I have an initial velocity vector here. This is from where I've initially launched it. I've got horizontal variables and I've got vertical variables. So I'm just going to start out labeling some basic things. We're going to say this is our ground down here. We're going to start with our compass just like we always do when we draw a vector. And I'm going to say that these two directions are positive and these two directions are negative. I'm not going to say whether they're north, south, east, west right now. That doesn't matter. Just that they're positive and that they're negative. And I'm going to say that this right here is my starting point. So that's where I'm going to start this from. And I already said at the top of the paper, this angle right here is theta, and it's our launch angle. All right, so we're going to start with the horizontal variables just because there's fewer horizontal variables than there are vertical variables. All right, so the first horizontal variable we have is our displacement on the x-axis. Same variable we would see in kinematics. This is how far it moves. The way you're going to see this worded in problems most of the time is its range. How far does it go? So at the starting point, our displacement on the x-axis when we start is going to be 0 because we haven't gone anywhere. When we reach the midpoint of this parabola, our displacement of x is 1/2. It's halfway to its final location. Our total displacement of x, or the number we're actually looking for, its entire range, is the point where it lands. So this point where it lands is going to be our final, or our total displacement of x, and that's right here. That's our range, or how far it goes. So if you're looking at an entire range, or an entire displacement on the x-axis, you're looking at where it starts and where it finishes, or this entire bottom. All right, the next variable we're going to look at is its initial velocity on the x-axis. All right, so we have our initial velocity here. This is when we were launched. So this is our initial vector right here, and I'm going to label this vector 1 because that's my initial velocity. And we've been working with dividing those initial velocities into x and y components. So just like any other vector, I can divide this into an x and y component. So my y component is going to be my up and down component. My x component is going to be this component on the bottom. So this right here, I've run out of room. But this is my velocity of x. And velocity of x doesn't change. So I can draw this in a few different places on my graph, and it's always going to be exactly the same distance. That velocity of x will never, ever change. So when I get down here to the very bottom, my final velocity of x is going to be the exact same as my initial velocity of x. So we don't have to have a final and initial here. We can just say the velocity of x. All right. And to kind of help us out, I don't think I actually wrote this. This arrow right here points to our max height. So this is how tall it's going to get. All right, so now let's talk about those vertical variables. There's lots of vertical variables we can talk about here. We're going to start off with some easy ones that are given. Acceleration only affects the projectile when it's going up and down. So this is acceleration. And acceleration is always 9.8 meters per second squared. And since we said that the downward force was negative, I'm going to give this little guy a negative up here. All right. I have velocity initial y. So this is my initial y velocity. And I am writing all this in the wrong color. I should be writing all this in green. I'm sorry. Our initial y velocity is the y component of this initial velocity. So this right here is going to be my velocity initial y. And I just said that as the vector changes along its path, that x velocity was always going to stay the same. All right, but let's look at this y velocity as we go along. When I drop it here, here's my velocity y here. I can drop a y vector here. This is my velocity of y here. I can actually drop one here. What do we notice about all of those? They're all different heights, or they're all different lengths. So this y velocity will change along the path. So your velocity of y will change along the path. And eventually you will get v2y, or your final y velocity. And that's going to be this one at the very end. And it actually is going to extend beneath the ground. Because remember, when something hits the ground, it still has velocity. It's not zero. It still has velocity when it hits the ground. What's really important here, though, is that we notice something. And this vector right here is straight along the x-axis. So when we reach this max height, our velocity of y is 0. Because there's no vertical components here. It's only traveling horizontally. So for this one moment in time, our velocity going up and down is 0. All right? And that will also give us the last variable we need to know that's a vertical variable. And that is the displacement vertically. Or it's max height. And that's going to occur right up here at the top. There's one more thing we haven't talked about that was a kinematic variable. So we've got displacement, we've got velocity, we've got acceleration, we've got initial velocities and final velocities. The one thing we're missing is time. And time is a unique variable when it comes to doing two-dimensional projectiles because time transcends direction. So time is considered both an x and a y variable. So time transcends direction. And we can actually use time as our variable to link horizontal and vertical. So time helps us go between horizontal and vertical variables because it can transcend them. So when we look at the starting point, our change in time is 0 because it's just being launched. When we get to the max height, our change in time is 1/2. We're halfway there at our maximum height. And then way over here at our landing point, we would have our change in time final. All right, last but not least, there's one last thing we can look at, and that's this angle right here. So because of algebra, we can say this launch angle is equal to the angle at which it hits the ground. We can take this final vector and get our final y, and our velocity of x is always going to remain the same. Also, I'll wait for the next slide for that. So these are all of our kinematic variables when we apply them to two-dimensional projectile motion.